All right, guys, we're going to talk today about exponential functions. We're in our new unit here. It is actually exponents and logs all together in one unit, but this first section is just on exponential functions. So exponential growth is the first thing we'll talk about, and that's an exponential function where the graph increases, which is just another word for grows, from left to right. It occurs when the base of the exponent is greater than 1. And then exponential decay is an exponential function that decreases from left to right. It occurs when the base of the exponent is less than 1. Okay, and then lastly here we have our natural exponential function, and so I'll draw a little arrow right there. And so this is f of x equals e to the x, and so that is an exponential function with this base of e. And the really important thing here is that e is actually not a variable. E is a number that is about 2.71828. It's an irrational number. It's kind of like pi, one of those weird numbers. It is very important for mathematics. We're going to talk more about why e is so important as this kind of unit moves on. But for now, just know that it's kind of this weird number, a lot like pi, and that it's about 2.718. Okay, next up we're going to get into some graphing here. And so for graphing exponential functions, I have kind of my steps for doing this. And so here are my main steps here. There's always going to be a couple key points. They're going to be 0, 1. And then there's going to be another one at 1, the base, whatever the base of the exponent is. And there's always going to be a horizontal asymptote at y equals 0. And we'll kind of see why that is as we go along here. But just remember that horizontal asymptote is at y equals 0. I would always put it y equals 0, not just 0, because that'll remind you that it's a y value, not really an x value. And then the next thing we need to really take care of is the transformations. And so we're going to be seeing a lot of transformations here. And so just keep that in mind. It's going to be a lot of the same transformations that we've been seeing. We saw a lot last unit. And you kind of been seeing them throughout your math career. All right, first up here, we'll do our first graph, and that's y equals 2 to the power of x. And so I'm going to use my key points back up here. There they are. And so we're going to use 0, 1, and then 1, base. But in the base here, we could see that the base is 2. That's kind of the thing holding up the exponent. So there's our 2. And we're going to start off with a horizontal asymptote at y equals 0. There's actually no transformations on this one. What a transformation would look like, you can kind of see it over here. If we have a negative somewhere, if we have a adding or subtracting like this, that's going to be our transformations. This one doesn't have any transformations, so I'm just going to draw these. So I'm going to draw my horizontal asymptote at y equals 0. I'm going to draw that first. That is kind of, you'd always draw that as a dashed line. An asymptote is kind of a line that's not really part of the graph. It's kind of just a guiding line that the graph gets closer and closer to but never touches. All right, for our actual points, we're going to draw them 0, 1, 1, 2. And so it's going to kind of go away from the asymptote as it goes that way, but approach the asymptote, let me draw that a little better here. Approach the asymptote. No, let me try one more time. There we go, that's better. Getting closer and closer, but it's never going to actually get there. And the reason that is, if you kind of think about this, is that 2 to the power of, let's say, like -2 is 1 over 4. 2 to the power of -3 is 1 over 8. So every time you make the negatives bigger, it's just going to be 1 over a bigger number. It's going to be a smaller and smaller number, but it's never going to actually get to 0. Okay, so let's do our next graph here. And so for this one, we're going to have 0, 1 again, but we're going to have 1, 1/2 now, because 1/2 is our base. And then we're going to start off with a horizontal asymptote at y equals 0. But on this one, we are going to have some transformations here. So our transformations Well, we got one for the x and one for the y. And so for the x, there's an x minus 1 up there, and we're going to put x plus 1 there. That is because x lies, so that's going to be a right shift there. And remember, it's always counterintuitive with those left and right shifts. And then this back here is going to be a down shift. So actually, why don't I label that? This is going to be a right 1 shift, and this is going to be a down 3 shift. And so I'm going to do y minus 3. So I'm going to take all my x values and add 1. And I'm going to take all my, and I'm just going from these points back here. And I'm going to take my y values and subtract 3. So 1 minus 3 is negative 2. And then 0.5 minus 3 is negative 2.5. If you prefer it like that, I think that's fine. Now, for the horizontal asymptote, that actually is going to transform. And this is why it's so important to have that as a y equals 0. So now I know that it's a y equals negative 3, since it is a y minus 3 there. Okay, so now we'll go ahead and graph this. So once again, I'll start with my horizontal asymptote at negative 3, and that's always a dashed line, not really part of the graph. And then we will say, what do we got? All right, 1 comma negative 2 there. And then 2 comma negative 2.5. And so this one, since that point on the right is closer to the asymptote, it's going to go away from the asymptote going this way, and it's going to approach the asymptote as it goes right. This also makes sense that it's a decay, because we see that whenever it's less than 1 for the base, that's going to be a decay. It's going to be decreasing, whereas the first one, greater than 1, was an increasing. All right, next up, we're going to go with our key points here on number 3. And so that's going to be 0, comma 1, 1, comma base, and a horizontal asymptote at y equals 0 to start. That's probably going to change here. So we're going to have our transformations now. And for our transformations, I definitely have up 1 shift. So it's going to be y plus 1. And then for this one, we have a negative up here. This is actually going to be a y-axis reflection, if you remember from your transformations. And so what that's going to affect is it's actually going to make our x's negative. So I'm going to switch the sign of my x's there. So this is going to become, well, obviously there's no negative 0, but this one's going to become negative 1. And I'm going to add 1 to my y values, and that means also to my horizontal asymptote. For those of you thinking, well, doesn't x lie? So it really lies on the adding and subtracting. With this one, it's just a y-axis reflection, so we do that by switching the sign of the x values. All right, so I'm going to make my horizontal asymptote at 1, so that'll be right there. And then we have 0, comma 2, and then negative 1, comma 4. And so that is going to decay like this. Now, why does that decay? Well, it should have been a growth because it's greater than 1, but it's really because of that y-axis reflection here that flipped. It would have been kind of going like this, but since it got flipped across the y-axis, it switched into a decay. All right, next up here, number 4. Now this one, I actually don't like how this one is written, so I'm going to rewrite this one as negative 2 times 1/2 to the power of x plus 4. And so that plus 4 is really, it's adding. It's just kind of adding in a different way. I kind of think of it like 4 minus 2x is the same as negative 2x plus 4, but I kind of prefer it written like this. I did write it the other way, so you can just get some practice seeing that. So our points here are going to be 0, comma 1, and then 1, comma base. Our base here is going to be 1/2. 1/2 has the exponent, 2 does not. And then our horizontal asymptote at y equals 0. All right, and so now we'll do our transformations here. And so what are our transformations? Well, we actually don't have any for x. If you look up here in the exponent, it's just x there. But for y, we actually have 2. We have we have 3. And so we have here, this is definitely up 4, but then this one is 2 things. The negative is an x-axis reflection, and then the 2 is a stretch. But we can kind of take care of all of this by just kind of putting in here, I'm going to multiply my y's by -2, and then I'm going to add 4. And so you can kind of see that that's the two things going on outside. So my x's are going to stay the same, but my y, I'm going to multiply it by -2 and then add 4. So with that, it's going to come out to 2. 1 times -2 is -2, plus 4 is +2. 1/2 times -2 is -1, plus 4 is 3. And then my horizontal asymptote, well, 0 times -2 is 0, but then plus 4 is 4. So my horizontal asymptote this time will be up here at 4. And then I got a point at 0, 2, and then 1, 3. And so this graph is going to approach the asymptote going that way. They don't really classify this one as growth or decay. I guess it is increasing, so you might call it growth, but usually they don't even classify it in one of those two. All right, next up we're going to do our first one with E, and so let me show you how we're going to do these. So we're going to just start off the same way as we did, 0, 1, 1, base. Now for the base here, for E, I'm just going to use 2.7. Now, when you're graphing, that's going to be kind of close enough for you to kind of get it done. When we're actually solving more important problems with money and stuff, we're going to have to use actual E. But for now, for graphing, we could just use 2.7. Okay, so we'll do our horizontal asymptote is at y equals 0 to start. We do have some transformations here. So we have x minus 1 and we have y minus 4. We got the x lies up there. All right, so it's going to be -1, -3. This one will be 0, let's see, 2.7 minus 4 would be -1.3. And our horizontal asymptote is going to move down to y equals -4. So -4 is down here. And then we got -1, -3. 0, -1.3. And there you go. Oh, I haven't talked about domain and range. Let me make a quick note of that here. So for domain, actually on every single exponential function, the domain is -infinity to infinity. So that's kind of a gimme right there. You can see that my graph does go left and right forever. The range is always based on the asymptote. So since the asymptote in this case is at -4, I would say this goes from -4 to infinity. And I would say that's a parentheses on the -4 because it never actually gets to that point of -4. Remember, that's the big idea of the asymptote, is it never actually gets there. All right, last up here for graphing, we'll do another E. And so we got a 0, 1, 1, base, which is going to be like 2.7. Once again, we're kind of estimating that one. And then a horizontal asymptote at y equals 0. And then our transformations here, we have an x minus 2 since x lies. And then for y, we're going to have to do -y plus 3. So if you have kind of something multiplying in front here, like a -1, or we saw earlier a -2, just apply that to the y. It's going to flip it upside down. Okay, so this will be -2, and then this will be -1. And then for this one, I have -1 plus 3, that's +2. -2.7 plus 3 will be 0.3. And then my horizontal asymptote will be at y equals 3. So I'll draw my horizontal asymptote up here at y equals 3. -2, 2, -1, 0.3. And so this one will approach the asymptote going to the left and then run away from it as it goes right. For domain and range on this one, once again, the domain for every exponential function, whether it's e or 2 or anything, will be -infinity to infinity. The range here is still going to be based on the asymptote, but in this case, it's actually going to be -infinity to, what is the asymptote at, 3? Because from here, you can see it goes down forever, and then go to the highest point is 3. All right, now we're going to work on some compound interest. And so here is our function right there. And so we got to know what all these kind of variables mean. So A is the amount at the end. And then P is called the principal, which is the amount at beginning. R is the interest rate, and that's got to be as a decimal. So we're probably going to have to convert that. T is time, and time must always be in years on this one. N is the number of times compounded. So if it's annually, that would be 1. If it's semi-annually, that would be 2. If it's quarterly, that would be 4. Okay, so here we got number 7. William wants a hot tub on his deck, and it's going to cost him $4,000, and he wants to get this in 2 years. And so he finds an account that pays 5% interest compounded monthly. So I already know R here is 0.05, and then compounded monthly would mean N is 12, because if you do something monthly, you do it 12 times per year. We know T is 2. And then kind of the weird thing here it says is how much must William put in this account? And so it's asking for P. We want to know what P is, and it's saying we want to end up with $4,000. So it's kind of backwards from how it's often done. It's okay, we can still solve it like this. So P is our unknown, so I'm just going to plug in everything else. Remember when we have A of T in here, if this is 4,000, we're going to plug in for that whole thing. So I'm going to say 4,000 equals, P is unknown, so I'm going to leave it as a variable, 1 plus 0.05 over 12, just following the formula there. And then this will be times, or sorry, to the power of N times T, so 12 times 2. Okay, now P is multiplying this whole thing right here, and so before I type anything in my calculator, I'm just going to divide this thing over to this side. And I'm going to go ahead and switch this to 24 right there. And I'll do the same over here. And so I like to do that just so it's all in one calculator kind of stroke here. We'll cancel these out, and this will just tell me what P is. And so I'm just going to type this in my calculator. I'm going to pause it right here. So if you want to pause it and type it into your calculator as well, make sure you know how to do it. Make sure you do those parentheses in the same spot that I did them at. That's very important there. And I get here that this is 3805.31 if I make it to the nearest penny there. And so that means he's got to save $3,800, a little over $3,800 if he wants to end up with $4,000. So this makes sense that it's less. P should always be less than A because I'm going to put in a little bit of money into my account and I'm going to get out a little bit more. I always tell people this about interest, is that interest is not going to kind of make you rich here. You can see that investing in this account for 2 years only gives them an extra $200, but it is money for nothing because you just put your money in the bank account and it sits there. And like I said, they're not going to give you a ton of money. They're just going to give you a little bit of money, but once again, it's better than nothing. All right, next up here, they're saying a sum of $1,000 is invested. And so that's our P here. They are telling us P. And then we know our interest rate is 0.011, so we've got to move that decimal place twice. So don't do 0.11, that would be 11%. And they're telling us that T is 3. And then they're giving us several different N's here. So for part A, N is semi-annually, so that's twice a year. Monthly is 12, and then daily would be 365. I know there's leap years and stuff, but let's just kind of forget about that and let's just use 365, okay? And on all of these are asking us what is A. So for part A, I would set it up as A equals 1,000 times 1 plus 0.011 over, what is that? This one would be 2 to the power of 2 times 3. And so I'm going to go ahead and just put 6 up here. And that was the 2 times 3 since it's to the power of NT. And then so I would type that in the calculator. I'm just going to set all of these up, and then I'm going to type them all in the calculator and see what I get. So then the next one would be 1,000. Everything's going to be the same until we get to N, because now we're going to do it as, let's see, 12. And so 12 times 3 would be 36. All right, then part C, 1 plus 0.011, and now it's over 365. And then 365 times 3, I'm going to use a calculator for that right now. Don't know that one in my head. And that's 1095. Okay. Cool. So now I'm going to start typing these in the calculator. I'm going to go ahead and pause it and do all my calculations here. If you guys want to pause it as well and check that out, I'll be back in a sec. All right, so what we get here is for the first one, I got 1033.46. The second one, I got 1033.53. The third one, I got 1033.55. So all these answers are very similar, and that's I kind of wanted to show here that when you compound at different amount of times per year, the answers do change, but especially at a low interest rate like this, they change very little. But the overall trend I'm seeing, and the question I would ask you right now to consider for yourself is, would you rather them compound it more often or less often? And so I'll give you a second to think about that. Would you rather have the bank compound your interest more often or less often? And as you look at your answers here, I think you should see very clearly that you would rather have them compound it more often. And so that is true. You can see that the 365 is better than the 2. And so would you rather have them compound it every day? Yeah, but what if you could do every hour? That would be even better. Or every minute, that would be even better. Or even every second would be even better. But there's actually the best way to do it is compounded continuously. And you can see that spelled over there if you can't read my writing. So for continuously, that's more than every second. It is just every instant, constantly being compounded. And when that happens, this is the formula. It is A of t equals P times e to the power of RT. And so that's where that e comes in here. Is that it is the formula when it gets compounded continuously. So we'll start using this formula now. And so we'll do this one. James buys a sound system for his car. It puts $5,000 on his credit card, and his card charges that much interest compounded continuously. And that actually is a reasonable interest rate for credit cards. Credit cards charge a lot of interest. That's why they're kind of the worst kind of debt to have. And so he's going to do this for 6 months. Now, this means t is 0.5 because, remember, t has to be in years. So the 6 months is half of a year. And that means he's borrowing $5,000. So let's see how much James owes after only 6 months of this. So that's 5,000 times e to the power of 0.1999 times 0.5. And so when I type that in, and one more thing on this one. For this one, for E, you can't use 2.7 anymore. It's not accurate enough. So you have to actually use the E button on your calculator. On most scientific and graphing calculators, it's second and then ln would be e to the power of x. And so you could type that in there. And so when I type that in, I get 5525.58. And so James is going to owe an extra $525.58 if he doesn't pay that credit card off. So in just 6 months, he's already owed an extra over $500. And so at those high interest rates, when you have a credit card, that's where interest can really hurt you. All right, next up says how much should be invested if Rob wants to end up with $3,000. So they're telling us A, and they're asking us for P. And so they tell us this is 0.03 for our interest rate, and then T is 4 years. All right, so I'm going to say 3,000, and it's compounded continuously. So that means we use our PERT formula. And this will be 0.03 times 4. And so I'm just going to divide that over. Once again, use the E button on your calculator here, not not 2.7. And so I can get it here. And I get 2660.76. So that means if he invests $26.60 now, he'll have $3,000 at the end of 4 years. All right, that's it for today. Coming back tomorrow for some more of this.